So our final set of presenters, again keeping up with the theme of electrical validation and protocol testing and validation. Godfrey Kulo from Prodigy Technovisions. So Godfrey founded Prodigy. You're going first, sorry. So I'll have Pratik Setumadhavan from Tektronix who's going first. Pratik essentially is a business manager for high-speed solutions for Tektronix. And he has been with Tektronix for the last 7 years in various sales and marketing positions. And he's presently responsible for high-speed and RF solutions in India. Go ahead, Pratik.
Hello everyone, thanks a lot for being here. My name is Praseeth, and over the next 30 minutes, we're going to be talking about the most common challenges faced by folks working on IoT devices. We'll be splitting it into 2 sessions. I'll be taking 15 minutes. And towards the later part of the session, we'll be talking about specific SD challenges. We'll cover a little bit about the electrical spec and different solutions that exist today to do compliance testing. So, any IoT related presentation, you're going to have a slide like this talking about the billions of devices that are going to be there by 2020, 2025, 50 billion, 60 billion, and so on. Now, such a trend of explosion of IoT devices, it's going to lead to a different kind of IoT, something we like to call the interference of things. If you look at this screen here, this is something that we've taken in today's environment. Okay, maybe a couple of months ago, but something that we can expect in any room today. You're going to have 3-4 different Wi-Fi modems running around, then you have some Bluetooth signals, and in this particular case, there was a microwave oven which was interfering with your Bluetooth device. And it was not something that they were expecting to see. This was something that they had to debug, and it's a very rare, very infrequent event that happens. Now just extrapolate it to a 50 billion devices. In your home, you're going to have your refrigerators, washing machines, your curtains, each window is going to have a chip on them, and all of them are going to be playing around in a kind of a limited spectrum. So you're going to have a lot of problems in doing that compatibility testing, and this sort of interference is going to be a common theme that you see going forward. Another thing I want to mention is the real-time performance that you see on the screen here. If one small tweak or some small blip is enough for your device to lose your data, right? So your traditional equipment, as of now, your traditional test equipment, it's not really built to support that kind of a system. If you're having a small slowly sweeping spectrum analyzer that you generally see, if something happens in a different frequency, you're going to totally miss it. So you're going to take a lot of time to capture and understand what is happening. So one, you need to move, most vendors you see are moving to improve the real-time performance of their equipment. And second, we need to make sure that this is available to the entire market by 2020, 2025. That involves a lot of reduction of cost. Because if every home is going to have this sort of a situation, your maintenance engineer is going to have that sort of equipment in his arsenal and that kind of technological education as well. Another common issue you'll see in IoT, the design space, is going to be the EMI compliance. So any platform, if you need to get it validated, get it out into the market, you're going to get it certified, right? Typically that takes around $10,000 per platform. It could vary based on where you are and what exactly your device does. And that is $10,000 if you get it passed in the first go. By God's grace, God forsake, if it doesn't happen in the first go, you're going to have to go back, rework on the device, and this is a very expensive proposition, be it whether you're an MNC or a startup. Expense both in terms of money as well as the time that is spent on this. So it's very critical that you have a pre-compliance setup in-house so that you're 100% sure that when you go there, you're going to get it passed in the first round itself. Now, the main hesitation that people have in getting the pre-compliance setup in-house is that your EMC pre-compliances, that device is pretty bulky, very expensive, and you can't really use it for many other things that you might want to do in your lab for your compliance testing and all of that. So cost is an issue, and of course you're not going to carry it out into your field for field testing as well, right? So typically people are looking for something that is portable. You can do your customer demos, field testing, wireless compliance testing, EMI. If everything can be done in the same instrument at a low cost, which is comparable to that $10,000, that's going to be a huge value add for the market. All right. So this is something that is existing today. It's about 600 grams. If you have big enough pockets, you can, in your cargo pants, you can stuff it into your cargo pants and do a lot of testing. Along with your tablet as well, you can do a lot of shit. So this is the kind of software, freeware, that is available to do your EMI pre-compliance even today. So if you work on IoT, this is somewhat of a typical block diagram that you're going to see in pretty much any device. It's a very, very basic block diagram. You've got some sort of a wireless module here. It could be Wi-Fi, Bluetooth, some of the other technologies that were mentioned today, like TransferJet. Could be anything, something that does your wireless communication. Then you have some bit of microcontroller here. You have some control signals going between those two. You have a power block. Of course, you'll have some memory and some FPGAs, DSP, all of that is going to be there, some interface buses. What are the typical challenges that you can expect to see in such a scenario? First, of course, you need to know whether your antenna is turning on or not. Then, of course, you need to look for antenna mismatch issues. So are these signals switching correctly? I have a clock here, so are the radiations from my clock affecting the antenna output? So there's a lot of things, concerns and issues that can stem out of this small block diagram. Now, the problem with respect to testing today is that this is a completely multi-domain environment. So you've got RF also coming into your embedded space, right? So typically to test your clock, you probably use a scope. For these, you will have typical protocol analyzers. Here, maybe it's a SPI bus sending some data. You're going to have some logic analyzers, which can do your protocol decode. And for the wireless section, you have a completely different equipment, maybe a spectrum analyzer that does everything in RF domain. So everything does its job very well separately. But if you want to see the codependencies, the time correlation between the different domains, it's very difficult. Just imagine one equipment working in the time domain, another one happening in your, debugging your RF signals. You got to trigger at the exact same time. It's a nightmare. So let me give you an example. I think RFID was mentioned earlier as an example, a key technology. So this is something probably everyone will understand as well. So just imagine there's a reader, an RFID reader, and a tag. All right. So how do you test this kind of a setup? So when they come closer together, they're going to communicate, and this is going to give its ID to the reader. Now connect one signal from your reader to the test equipment. That is the blue line, blue channel. The yellow is the tag. Everything you see in orange is the wireless activity that is happening between them. All right. Maybe an antenna is connected to the test equipment, and it's showing you in the frequency domain what's happening. So this is a very common look in any spectrum analyzer you'll see, where it's power versus your frequency. And on the top domain, it's in time domain. So this frequency, if you look at this yellow bar here, you can actually scroll over time and see what exactly this screen will change. So when this signal turned on. So here what is happening is, first your reader is enabled. Then it will send a signal to your tag. The tag will respond. Your reader gives an acknowledgement, and there is some data transfer happening between these two. And at any point of time, you can go and see what is happening in your wireless domain. You can scroll through, okay, go here, and then this signal changes. You see exactly, you can measure the power and do all sorts of frequency domain measurements in the same domain. Now, if you have to do this with multiple equipment, it's going to be very, very complicated, and you're not going to get this sort of a flexibility of looking at your entire system. To give you a better approach, this is what the system is going to look like. This is where your RF input, your antenna will fit in. You've got 4 analog channels like any oscilloscope, and you've got 16 digital channels. So that is 21 different channels that you have access to on one single piece of equipment. So say, for example, just imagine we spoke about EMI pre-compliance, right? So that just gives you a pass and fail. But if your device fails, what are you going to do about it? You need to come back and look at the complete system and debug what the issues are. So you get a chance to connect 21 different signals. You may have some USB bus that is causing a problem elsewhere with the antenna transmission. All of that you can connect to one single system and see the entire performance on a single screen. And there are a couple of videos that I could share with you later on, which shows how simple it becomes. You just connect everything, turn it on, and you see a codependence between different buses that are running on your board. Power consumption. So this is a key point for a lot of IoT applications. I won't say all, but typically starting from your phones to many power critical applications, you want to, so people try to reduce their transmit time to as low as possible, because in some applications you want to leave your device somewhere, someplace for 5 to 10 years. You don't want to bother about it, recharge it, nothing. And after 5 years you discard and put a different device. So there are many applications of that sort. So it's very important. So that's a value selling point for you guys. That's your value proposition when you go to your customers. When you can show a device profile and show how exactly your device is, going to behave through the 5 years. All right. So just as an example, even in your mobiles today, you have ultra power saving mode and maybe 3-4 different modes. So the main challenge with respect to test is that, say in deep sleep mode, when your device is completely at rest, it's probably drawing maybe nanoamps of current. And when you go to the other extreme and it's actually transmitting, it goes to a much higher range, hundreds of milliamps or a few amps even. So there's a complete range of current that you look at. The next issue is when you limit this to as low as possible. So you're going to be transmitting maybe for a few microseconds if you can help it. Now the problem is the devices that are typically used for such a current range, maybe your bench digital multimeters, they typically cannot go down to microseconds kind of a speed. They will have few thousands readings per second. So that's a huge challenge. So your DMMs can do this part of the job, and for transmitting part, you typically end up using an oscilloscope, because that's got a very high sampling rate, and microseconds, nanoseconds, picoseconds is going to give you all of that. But the problem is, on typical oscilloscopes, you do not have your probes that will support nanoamps and microamps of current. Max, you could go to 1 milliamp probably. So that was a huge challenge that most people were facing, even in the mobile space, even before all of this came about. People have had this issue for 3 to 4 years. Now, today in the market, we have bench DMMs that have a lot of inbuilt scope features. So you can trigger, you can see the waveform, and it's got very high sampling as well. It goes up to 1 megasamples per second. For this application, good enough. Automotive is a pretty big thing. I think a lot of tracks are going on around the automotive space. Even for flash memory, a lot of different kinds of application. Some, of course, the usual infotainment. In security, you need reliable GPS data, or in driver-assisted systems, there also you need a lot of memory. A lot of applications which have different requirements within SD memory itself, right? So what are the typical measurement challenges that you face with respect to SD testing today? One thing that will become much more important now will be the signal integrity. So you saw that the data rates have been continuously increasing, and now it's going to double now. So that's going to be more important now. Now the issue is that while testing, people tend to do just a functional check around here. In India, okay, I'm doing a functional check, should be good enough. But now with increasing speeds, it becomes more and more critical for you to go to the file layer and actually do a comparison check. So one problem that you would typically face is that nowadays you're seeing a different protocol team and different file team in different organizations. So you have a set of people who are doing protocol tests and a different set of people who test the file. And when there is an issue, there is always some sort of finger pointing going between, oh, this is a protocol issue or this is a file issue. There's not much of a clarity. So this is the same issue which you saw in the earlier slides, but just customized to SD. So there are ways of doing both protocol decode as well as file layer testing on a single instrument, the instrument being an oscilloscope. So you can do a protocol decode, and you can drill further. Once you see a protocol fail or some sort of an issue, you can drill down into the same signal and see the file layer characterization and different electrical specs, and you can check what the actual issue is. Now, some of the limitations of using an oscilloscope, there are some limitations, apart from the cost or all of those factors. One is definitely the memory. When you're doing a compliance test, you ideally want to capture as much as possible, right? You just don't want to go just look at one command. You need to capture as many commands or responses as possible. So that is a limitation that we've been working on. There are a couple of ways to do it. One is, of course, increasing the memory of your scope. That has been tremendously improved. But the better way of doing it is how to optimize that system. One is called fast frame. So typically, after a command, if there's a huge idle time where there is no transition at all, typically your scope in a normal mode it's capturing all this useless junk data, right? So using fast frame, you can set your instrument in such a way that only the active period of time, only that is actually captured. So all this idle period, it's eliminated, it's properly time-stamped, and you carry on. So with that, you get to capture much more data in the hundreds of commands you can do. This is my last slide. Another thing that optimizes this kind of data is the protocol awareness of this oscilloscope. So if your scope can actually identify when exactly you want to trigger, you don't have to capture any other kind of junk data or anything else. So if you're just looking at command, you can actually enter all the different parameters that you're looking for with respect to SD, and you can trigger just on what exactly you want to characterize at that point of time. So this, it's from a company called Prodigy Technologies. So the second part of the session will be taken by my friend Godfrey right here. In the meanwhile, any questions?